In this video, we're going to be looking at an example where we have three objects that are going to be dropped from some height, or released, I should say. Now, in this is a very specific type of example. We're going to be looking at conservation of mechanical energy. Remember that conservation means comes from conserved, meaning that the total energy will be equal before and after. The reason that we say that energy is conserved is because that there is no friction or no air resistance. So there's no outside forces that are going to be acting on these objects. We have three objects. In this case, they're some type of ball, bouncy ball, softball, soccer ball, doesn't matter. And they're all going to be released from the same height. So if they all have the same height of 5 meters, and they all have the same mass of 3 kilograms, then they're all going to have the same potential energy, because remember that gravitational potential energy is equal to mass times acceleration of gravity times height. Another thing in this example is that we're assuming that they're released from rest. Because they are released from rest, our initial velocity is 0. And so if we were to look at the initial kinetic energy, it's 1/2 times the mass times the velocity squared. And if our velocity is 0, that means that our initial kinetic energy will also be 0. So as we look at these three, we have an initial kinetic energy that is 0 for all of them, and they have some gravitational potential energy. And we said that the gravitational potential energy for all three of these is the same because they have the same mass, 3 kilograms, they have the same height, 5 meters, and g is a constant. G is acceleration due to gravity, 10 meters per second squared, and it does not change. As this ball here falls to the ground, its height is going to decrease as it's falling, and as its height is decreasing, its velocity is going to increase until that instant when it reaches the ground, before the ground stops it. At that moment, it is going to have its maximum velocity. Because it has its maximum velocity, it will have its maximum kinetic energy, and because it has its maximum kinetic energy, that means that all of the gravitational potential energy will have been converted into kinetic energy. I've summarized our 2 points of interest by using these stars here, and we set up here V equals 0, so K equals 0, H max, gravitational potential energy that is max, and as we just discussed, at the bottom here, we have velocity that's maximum kinetic energy, height equals 0, so our gravitational potential energy equals 0. When we look at the second hill, nothing has changed for this ball B. This point here is still the same that we started with. We have the same height, and the point at the bottom is still the same as well. We won't see any changes in terms of the transfer from gravitational potential energy to kinetic energy. Both balls will still reach the ground with the same velocity. The only difference is the time that it is going to take for those two balls to reach the ground. So in case A, it is going to have a much greater acceleration, so it is going to reach the ground in a shorter amount of time, and it's going to reach some Vmax. Ball B will have a longer distance to travel, so it's going to take a longer time that acceleration is acting on the ball, and assuming no loss due to friction, which we said at the beginning, even though it reaches the ground with the same velocity, it's going to take longer. So maybe in case A, it's going to take 1 second to reach the ground. In case B, it might take 3 seconds to reach the bottom, but it will still reach with the same velocity as ball B. Lastly, in case C, it's still the same as in A and B. We still start from the same height, and we are still going to end at the bottom of the hill. So we still are going to have the same exact change that we had in A and B in terms of our conversion from gravitational potential to kinetic. All right, we still have the same change in height. Once again, the only difference, because it's at a shallower slope, it's not as steep as B, it is going to take longer to reach the ground, but even though it takes longer, it has a smaller acceleration, but that acceleration is acting on it for a longer period of time. Therefore, at the bottom, it will still have the same velocity as in points B and A. We said in A, maybe it took 1 second to reach the ground. B, it took 3 seconds. Here, maybe it'll take 6 seconds to reach the ground, but it will still be reaching the same Vmax as in scenario A and scenario B. In this example, we have a ball that is released from the top of a hill. We know the height of the top of the hill. In this example, it's 12 meters. We know the mass of the ball is 5 kilograms. We know the initial velocity because it's released from rest. Once again, our initial velocity is going to be 0. The only thing that we don't know is going to be the final velocity. So in order to kind of fill out this chart here, we need to know the total mechanical energy. And remember that mechanical energy is the sum of the gravitational potential plus the kinetic energy. Because we're not given the information at the top and bottom here, we're only given information in between, we got to go somewhere. We could start at the bottom here. However, we know the gravitational potential energy is going to be 0 because there's 0 height at this point down here, but we don't know what the kinetic energy is going to be because we don't know the velocity at this point down here. So if we look at the point at the top, we know the kinetic energy is going to be 0 because it has 0 velocity when it's released. And we can calculate the gravitational potential energy using that formula that we had before, which is GPE equals mass times acceleration of gravity times height. I went ahead and filled in that information that we discussed, and I solved for the gravitational potential energy, and I got 600 joules. Because we said that energy is conserved, because we have no outside forces, we know that the initial gravitational potential energy is going to equal the final kinetic energy. So if we come down here, we can fill that in, and it will be 600 joules as well. To find these other 2 points that we don't yet know, we know that the total is always going to have to equal 600. So if we look at point B specifically, the kinetic energy is going to be equal to our total, 600, minus the information they tell us, 420, all right, and we are going to get 180 joules at that point. Looking at point C, we're given the kinetic energy is 380 joules, so once again we do our total, 600 minus what's given to us, 380, and we are going to get the gravitational potential energy at that point is 220 joules. To recap, we were not given our starting or ending energies, but we knew that energy was conserved. We found the initial gravitational potential energy by using mass times gravity times height, which was 600 joules. The initial kinetic energy at point A was 0 because the ball was released from rest and it had 0 velocity. As the ball went down the hill, its height decreased, therefore its gravitational potential energy decreased, and as that height decreased, we had energy that was converted to kinetic energy because we saw the velocity of the ball was increasing as it rolled down. It had its maximum velocity at point D. The height was 0, so we see the energies flip-flop. We have all of the gravitational potential energy being converted into kinetic energy, so we're left with 0, and we know that as well because we have no height. To find our points in between, when we add them together, the sum always has to equal our total energy, which was 600 joules.